Hello engineering students, this is Mr. O and I'm going to go through uniform distributed loads, and this is an introduction to them. So what I have is a question which says, determine the reactions at the supports of the simply supported beam and include a force diagram with your answer. So the question has, and I'm going to redraw it so that I can get understanding of it very quickly. Nothing special in there. It doesn't say the question doesn't say that the beam is unbalanced, so I assume it's balanced, and then I draw it. So let's have a look. I have a fixed or pin support on the left hand side and a roller support on the right hand side. Now what this has as well, instead of standard forces pointing downwards, so what we call the normal forces or the equivalent concentrated loads, as you would also probably call it, we have instead two uniform distributed loads. And I'm drawing them like this as to where they start and where they end. My little drawing might be out of scale, so I apologize for that. And so we have a uniform distributed load which starts about 2 meters from the side, from the far left hand side, and goes for 2 meters. So it starts there. And as the saying goes, it's a load that is distributed uniformly across this length of the beam. I have another one, which is uniformly distributed to the end of that beam, starting from 4 meters from the right-hand side of the beam. And I've got my rest of my... So this gives me a good idea. I have a 2, 4, 6, 10 meter long beam. Okay, on the left hand side I have a fixed or pin support. That tells me straight away I'm going to have two forces that it is going to apply to this beam. I'm going to assume they're upwards. This is my reaction on the left, and so it's going to be a force on the left horizontal and a force on the left vertical, because it's a fixed or pinned support. The roller support only applies a force, I'm going to assume it's positive, a vertical force. So this is my reaction on the right, and I'm going to call this force right vertical. So back to my two uniform distributed loads. There's something else that they say here as well, that they are 4 kilonewtons per meter. So the load applied to this beam is 2 kilonewtons per meter. This one is 3 kilonewtons per meter. How you solve this is you actually resolve these to a single concentrated load or a single point load, a normal force acting at 90 degrees. How you would do that is you would work out how long is this UDL. This particular uniform distributed load is 2 meters long. So I have, and it tells me, I'm going to call it UDL1. I'll just put a little number 1 there. It is 4 kilonewtons per meter. There are 2 meters long. Therefore, my total force downwards is 4 times 2 is 8 kilonewtons. Do you see how I got that? But where do you put the force? Because technically, what I have is I have a beam and I have a force that is spread like that. It can also be represented like this, with arrows pointing downwards, saying there's a UDL there. What we do now is we work out what is the middle of that UDL, which is going to be half of 2 is 1, and it's 2 meters from the left, so it's going to be 3 meters from the far left hand side. So let me draw that again. Here's my little, this is 2 meters to there, and it's 2 meters, if you look closely, 2 meters, 2 meters. The center of that is going to be half of 2 is 1 meter, so it's going to be 3 meters. So what we do is we work out what the total is, and we actually make that a single concentrated force downwards. And that is actually of 8 kilonewtons. I'll do the UDL2 as well. Hope you can see that. UDL2 is 3 kilonewtons per meter. Sorry, 3 kilonewtons per meter. Technically, I'm going to rewrite this so it makes sense. 3 kilonewtons per meter times 4 meters long. Those two cancel out, and it becomes 12 kilonewtons. If we want to stick to the maths as accurately as we can. To find out where that equivalent concentrated load or that point load or normal load at 90 degrees is to that one, we just halve the distance of that. So we know that here's the end of that one. This is 4 meters. Half of 4 meters is 2, so it's going to be 2 meters from the end. If we take a moment from the left-hand side, as we're going to do to resolve these, we take a moment. It's going to be 4 meters less 2, so it's going to be 4 meters less 2 is where that is at 12 kilonewtons at 8 meters from the left. Do you see how I got that? 2, 4, 6, and half of 4 is 2 because it's in the middle. It gives me 8 meters. So let me briefly just redraw this so that it makes sense. I'll redraw this. What we're working with now is really that and that. And the distance is 3 meters. As we worked out, half of 2 is 1, plus the 2, so 3 meters across. Half of that 4 of the second one is 2. The total beam length is 10, so it's effectively 8. 2 meters plus 2 meters plus 2 meters from its start. Halfway across is another 2, that's 8 meters. So there we go. And this is 8 kilonewtons and 12 kilonewtons. And that's how I then move to my next stage of solving my reactions, the supported reactions. So I'm going to do a really quick calculation. I've just showed you exactly how to solve these. It's basically telling you 4 kilonewtons per meter. It's 2 meters long, therefore it's 8 kilonewtons pointing downwards. 3 kilonewtons per meter, it's 4 meters long. 4 times 3 is 12. That's it. And then you just divide by the distance so you know where it is, and you'll work out how far it is from where you're going to take your moment point from. Quickly do my assumptions. Clockwise is positive, counterclockwise is negative. Up in my vertical force is positive, down is negative. To the right, my horizontal force is positive, and to my left. That's kind of my assumptions just done pictorially. So let me just do this quickly. I'm going to do a moments around my fixed, because I know I'm going to have that, I'm going to have that, I'm going to try solve. So I'm going to solve for the force right vertical, force left vertical, force left horizontal. That's the reaction of that side, and that's the reaction of that side. And my uniform distributed loads have been simplified to a total load at a certain point, 8 meters from the left and 3 meters from the left, 2 and 1 respectively. Okay, so I'm going to take moments. The sum of the moments equals 0. Moments equals force times distance. And I'm going to go 0 equals plus force times distance, clockwise, minus force times distance, counterclockwise. At that point, I've got 1 and 2 forces forcing that beam to pivot on that moment point, and 1 pushing it counterclockwise, 2 pushing it clockwise. So I go plus force times distance. Oops. Force times distance minus force times distance. Clockwise, counterclockwise. Remember, the sum of all the moments equals 0. The sum of all my clockwise moments and the sum of all my counterclockwise moments will be negative, and those will be positive. Let me solve this one. I'll start by going from the left. I've taken a moment around, and normally I'd state that. I take a moment about RL to find RR, which is a force right vertical, because it's a support, roller support only. Let me go straight up and look here. Force, that's going to cause a beam to go clockwise. Kilonewtons, kilonewtons, I check the units, they're all the same. Meters, meters, they're all the same, so I can probably remove all of the units in my calculations to make it simpler to read. 8, I'll put them in when you're doing your calculations. Just start far on the left hand side so you have the space. 8 times 3, because it is 3 meters away, plus 12 times 8. Remember, we had 2, 4, 6. Half of 4 is 2, so it's 8 meters away from the far left hand side. Subtract 10 meters, but the force is the force right vertical times 10 meters. This is when your simple calculation, and maths comes through. So 24 plus 96 minus 10 FRV. You guys happy with that? I hope so. I can't hear you, but it's all good. And that's a really sad dad joke, that. Okay, 24 times 96. What am I doing? 24 plus 96. I should have done that on my head. Minus 10 FRV. I'll take that to the other side. It becomes plus 10 FRV equals 120. You can see it's pretty simple. "12 kilonewtons, the force of the right vertical." And it's positive, therefore it is pushing up. So my force upwards is 12 kilonewtons. And that's it. Effectively, I've just drawn a little line here. Once you found out where the center point is, and you've been able to solve where the equivalent concentrated load or the center of each of those uniform distributed point load is, or normal force at 90 degrees, it becomes a standard, nice and easy, simple beam question. And it's really, really not that hard. I'll finish it up quickly. My force horizontal, well, I don't have any angled loads. I only have vertical loads. So my force horizontal is 0. My force vertical, technically, the sum of all my forces vertical should equal 0. So to solve that, I go sum of the forces pointing downwards equals sum of my forces pointing upwards plus EF upwards, because that goes to the other side, because that's a positive. They're both positive, but when this goes to this side, it becomes a negative. Sum of the force downwards. So let's work them out. I've got one force upwards and another force upwards. I know what that one is, I don't know what that one is. So my force upwards is going to be 12 kilonewtons. I've already solved that one. Plus force LV, I've already solved the horizontal. Minus the two of loads, 8 plus 12. So what is that? 12 kilonewtons plus FLV minus, what is that? 20. FLV minus 8 plus 12 minus 20 is 8. That goes to the other side. 8 kilonewtons equals FLV. So to prove that with my really simple, this has asked me to do a basic force diagram, just like kind of what I've done there. I draw my beam. I've solved that already, which is 12 kilonewtons. This side is 8 kilonewtons, and really you can see how simple it is. They cancel each other out. It makes perfect sense. You don't have to. It's probably good to put that in. Okay, that's the question done. That's a simple uniform distributed load, just showing you how you take the force into the center. Basically the force times the distance of that uniform distributed load gives you the total load. So your uniform is, I'm going to write that here. There we go. That's how you solve this particular question. Hope that helped, guys.